1 in a million. That is roughly how often this particular decay happens inside the Large Hadron Collider. Out of every million B mesons produced in those collisions, about 1 breaks apart in a way the standard model only allows through a rare quantum detour. For more than 10 years, that decay has carried a problem. The numbers keep landing away from the clean standard model prediction. In December 2025, the LHCb collaboration at CERN released its most detailed analysis of this process so far. It used more data than previous measurements, tighter controls, and a sharper reconstruction of the decay. The tension with the standard model is still around 4 sigma. In particle physics, 4 sigma is already serious territory. It is below the official discovery threshold, but well past the point where physicists can just shrug and move on. So what is a B meson? Why does this 1 in a million decay matter? And why are physicists still arguing about it more than a decade after the first hint appeared? A B meson is an unstable particle built around a bottom quark, one of the 6 known types of quarks, paired with a lighter antiquark. It lasts about 1.5 picoseconds before it falls apart. A picosecond is a trillionth of a second. On that timescale, the particle barely exists at all. But its decay can still be measured, and in this case, the details matter. When the LHC smashes protons together at close to the speed of light, it produces huge numbers of B mesons. Most decay in ways physicists understand extremely well. Those ordinary decays are part of the reason the standard model has such a brutal reputation. Again and again, it predicts what nature does with ridiculous precision. This decay is different. Inside the meson, a bottom quark becomes a strange quark without changing electric charge. The decay also produces 2 muons. Muons are heavier cousins of electrons. They do not last forever, but in a detector they leave clean tracks, which makes them extremely useful. The final state is a kaon, a pion, and 2 muons. That may sound like a tiny technical detail. It is not. Under the simplest rules of the standard model, this transition has no direct route. The bottom quark cannot just turn into a strange quark in one clean step. That path is forbidden. So the decay has to go through a quantum loop. In the standard model picture, virtual W bosons and heavy virtual quarks, especially the top quark, enter the calculation. A virtual photon or Z boson can then produce the 2 muons. None of these intermediate particles show up as tracks in the detector. They are not little objects briefly photographed inside the machine. They are part of the quantum machinery that makes the decay possible at all. Physicists call this a penguin diagram. That is the real name. It came from a 1977 bet between 2 theorists. The loser had to work the word penguin into a scientific paper. Somehow, he managed it. The name survived, and now one of the strangest possible names in physics sits at the center of a serious problem. The loop is the reason this decay is rare. It is also the reason it can expose something the standard model may be missing. If unknown particles exist beyond the standard model, they do not always need to appear directly in the detector. They may be too heavy, too hidden, or too weakly connected to produce a clean new signal at the LHC. But a loop is different. A new particle can affect the calculation without ever appearing as a visible particle in the final event. It can slightly change how often the decay happens. It can alter the angles between the outgoing particles. It can leave a fingerprint in the geometry. LHCb is built for exactly this kind of work. It does not only hunt for spectacular collision events. It studies the small, rare, precise decays of particles containing bottom quarks. The new analysis used 8.4 inverse femtobarns of collision data. In plain English, that means a huge collision dataset, large enough to test this rare decay with far more precision than before. From that dataset, the team reconstructed the decay and measured the angles of the particles flying out of it. Those angles matter because new physics would not necessarily create a new particle on screen. It could simply bend the pattern. One of the most important measurements is called P5'. It has been central to this anomaly since the early LHCb results. P5' measures one specific angular pattern in the decay. The standard model gives a prediction. The LHCb measurements have repeatedly come out lower than expected. The latest analysis does not erase the old problem. It gives physicists the strongest version of it so far. Across the full set of measurements, the tension with the standard model is about 4 sigma. Sigma measures how unlikely it is that a result is just a statistical fluctuation. In particle physics, 5 sigma is the traditional threshold for claiming a discovery. The bar is set that high because many promising hints have disappeared once more data arrived. 4 sigma is below that threshold. It does not prove new physics. It does not allow anyone to say a new particle has been found. But statistically, it is already a hard result to ignore. Depending on the convention used, the chance of a fluctuation that large is in the range of tens of thousands. The harder part is theory. To know whether the measurement disagrees with the standard model, physicists first need to know exactly what the standard model predicts. That is difficult here because the decay is wrapped inside the strong force. The bottom quark is bound inside a B meson. The strange quark ends up inside a K-star meson, which then decays into a kaon and a pion. These are messy bound states controlled by the strong force, and the strong force is extremely hard to calculate in this regime. So the prediction depends on difficult details: the internal structure of the mesons, hidden strong force effects, and approximation methods that still carry uncertainty. Some physicists think those uncertainties could be wider than the published error bars suggest. If they are right, part of the anomaly may be absorbed back into the standard model. Others argue that the pattern is too persistent and too structured to dismiss so easily. That disagreement is the center of the whole debate. The anomaly first appeared in the Run 1 data. It remained visible when Run 1 and Run 2 were combined. Now the most comprehensive LHCb analysis so far still points in the same direction. After more than a decade, the problem is not just the size of the deviation. It is the fact that the same rare decay keeps putting pressure on the same prediction. A detector problem is still possible, but it would have to mimic a very specific pattern across years of data. A theory issue is also possible, especially because the strong force calculation is so difficult. The point is simple: this problem has survived long enough to deserve serious attention. CMS has reported a compatible result, although with less precision than LHCb. Belle II in Japan is important for a separate reason. It studies B mesons in electron-positron collisions, not proton-proton collisions. That gives physicists a different environment, a different detector, and a different set of systematic errors. If Belle II eventually sees the same pattern with enough precision, the debate changes. If the gap exists, the cause has not shown itself directly. It may be a particle too heavy to appear cleanly at the LHC. It may be a hidden interaction that only shows up in rare flavor-changing decays. Or it may still be buried inside the big difficulty of calculating the strong force inside mesons. But the problem for the standard model is simple. This is the same rare decay, the same kind of measurement, and the same direction of disagreement, more than 10 years later. A process that happens once in a million is still giving an answer that does not quite fit. And that is exactly why physicists are still watching it. There are books linked in the description that go deeper into the standard model and what physicists think may lie beyond it. I've also put 2 related videos on the end screen that connect directly to what we covered today. Thank you for watching. See you in the next one.